going to this talk. Hello, good evening. Nice of you to come out on this lovely December wet, cold evening to listen to me rant on about ADI again. But unfortunately, that's what I love talking about, ADI. So tonight's short talk will be about a Unimog 3-point linkage arm. This was developed by a company called Atkinson Vos, based up in Lancashire, along with Lancaster University, and then obviously ourselves, ADI Treatments, the Foundry, the Boro Foundry, and a machine shop called Partline. Okay. Evening. So what I'm going to do is talk about the design concept. So first of all, what is a 3-point linkage? Well, it's a part of an attachment goes on to, let's say, a tractor, but in this case, a Unimog machine, which is used for lifting things like wood chippers or other tools that you want either on the front of the vehicle or on the rear of the vehicle. And it's a very important part as it transforms all the forces and loads from the hydraulic cylinders into the linkage arm and the quick hitch. So there's a lot of load goes through this component. And when it's first designed, the design was obviously very simplistic, which was a metal fabrication made up of 9 pieces of steel. And when they put that into the field and lifted up some wood chippers, they found out that actually there was too much load on the part and they were starting to fail. So they actually added some additional parts of steel into 11-part component, weighed 55 kilograms, and it did the job in a manner, but it looked pretty awful. And if you can see there, the arms are at an angle. So where the hydraulic cylinder rams are lifted, they are sort of vertical and the arms are at an angle. So what would happen is they would actually seize up, and over a period of time, the hydraulic arms would actually bend because they kept being forced into an angle. So the customer, Atkinson Vos, looked at that and said, okay, we haven't got a perfect design. Let's see what we can do. But the best way we can do that is to make use of students. So they went to Lancaster University and said, okay, you've got some final year students here. Here's a project for them. Take our welded fabrication and come up with a design that works. So the first concept was to take the steel casting and basically copy it and make it into a cast version. And obviously, what they first did was looked at cast steel, because everybody knows cast steel. If you want something that's strength and got ductility, often they'll say, "Oh, we'll use steel." Unfortunately, first comes to mind isn't spheroidal graphite iron, ductile irons. It is steel. Fortunately, there was a student there who said, "Well, I know this material called ductile iron. I wonder if that would do the job." So they did some design work, and they came up with 2 options: the cast steel. And then they found this material called ADI. And the great thing about ADI was it was very light. They managed to make this casting 34 kilos. And everything looked great until Atkinson Vos pointed out that the arms were still at an angle. So the cylinders, the hydraulic cylinders, would still seize up over time. So they said to the students, start again, or not start again. Let's move on to concept number 2 and actually get it to work a bit better. So what they did is they came up with another design which allowed them therefore to design the arms in the same or parallel to the cylinders. So that obviously there wouldn't be any fouling or bending of the cylinder arms. However, when you did that, obviously the weight went up. So now the cast ADI was 54 kilos. Compared to steel, which is 64 kilos, and the original welded fabrication, which is 55 kilos. So the ADI was still slightly lighter and definitely lighter than the steel. So at this point, Atkinson Vos said, okay, we're looking now at the design and the shape looks good, but now we need to ensure that actually it will do the job. So let's look at some of the stresses and some of the factors of safety. So the first, got ahead of myself. Obviously, what we said was a design in ADI, and this is the grade that they decided to specify, ADI 908. This is a European norm or the ISO norm. You can see here the typical properties from a separately cast test bar. So this is a Y block of 30mm section, tensile strength of 900 megapascals, a yield strength of 600, elongation of 8%. There's also the ASTM standard, but obviously we're dealing here in the European customer, mainly for European market. Okay. Yeah. Next one. Yeah. Okay. So as I said, first of all was then where Atkinson Vos working with the university said, okay, we've got these designs. Now let's do some comparisons. Let's look at the factor of safety. So first of all, we look at the steel. And what we can see here is some very large areas, a lot of areas of red, which means they are not very secure, not very safe. They're likely to fail. That's likely to lead to points of failure. Whereas when we look at the ADI, you can see here the factor of safety is vastly improved. In fact, it's only a sort of 3 and above. So in the steel, we're having values of 1 to 3. With ADI, we're 3 and above. So it means that we've got a very safe looking component. And then we look at the stresses involved in the casting and the welded fabrication. So again, we look at the welded fabrication and we have stress values here on average around about 300 megapascals. Some of the welds would be up at 600. So some very high stresses at the welds themselves. And of course, if we're looking at 11 parts, we're looking at a lot of welds. So we're looking at a lot of places where cracks could initiate and failure could occur. Whereas if we look at the ADI version, we can see very, very low stresses. So now we have a component which has very good factor of safety, very low stresses. We have a component which is 54 kilos, so it's about the same weight as a welded fabrication. And not mentioned yet, is as cost competitive as the fabrication. So we can see now that when the Atkinson Vos and the engineers at the university looked together, they said, okay, now we have a component that we can safely say beat the steel fabrication with regard to factor of safety, stresses, the look and the way it's going to act in the field. We're not going to get the fouling of the lift arms. We're not going to get the potential failures down to the eccentric loadings. So we have a component that can easily be replaced. But this is all on paper or on computer, so we have to go to the next stage and actually make the part. Okay. So the first part is the casting, which is something that I sort of will leave to the experts here about how to cast metal. But we can see here, we're not talking about a high volume, about automatic molding lines. And we're not talking, obviously, we're talking sort of relatively large casting, 55 kilos, section thicknesses of the casting around 80 millimeters. But we're not talking hundreds, we're not talking thousands, we're talking tens, 20s, because it's a specialist vehicle and it's only a specific customers will require this attachment onto the vehicle depending on their business. So we go to a joint foundry and we talk with them about how to do this. And obviously the way they've gone about it is to use the floor molding with a basic alkaline phenolic sand. They poured at 1380. As you can see, even the casting weighs 54 kilos. The actual casting with all the risers and feeders was 88 kilos, so around about a 70% yield. The actual component itself was about 600 by 520 by 120. And there's a couple of adaptations. So, for example, we had to apply tie bars in. From the casting, you probably saw you've got these arms that come out. And obviously in heat treatment, those arms will want to move because as we heat parts up and cool them down very rapidly, they'll want to move in where to feel comfortable. So we have to prevent that. And the way we prevent that is to put it into a tie bar. And obviously the other thing you have to do is prove out the casting. And the most common way you prove out the casting is with separately cast test blocks. Now, although the casting section itself has a maximum of 80 millimeters, most of the forces and loads and issues they're concerned with are actually on the arms. And the arms are of the thinner section. So it was decided to cast Y2 blocks, which have a section of only 25 millimeters. So we weren't looking at the actual results in an 80 millimeter section, which would have been a Y4 block, Y4 block. We decided to just look at a Y2 block. Okay. For those of you who don't know ADI, we actually have to alloy the material depending on the section of the casting. Because the heat treatment involves a very fast quench into a molten salt, and I could talk a long time about ADI itself, but I'll keep it brief. Because it involves a quench into a molten salt, we have to add alloying elements to increase the hardenability factor. Now, we work with a hardenability factor of about 0.1 is when we're doing our calculations. That gives us sort of a margin of safety again, that we know that when we quench the component, it will, through quench, so the surface and the core will transform into the correct microstructure at the selected austempering temperature. And the way we do that is by adding hardenability agents. Carbon itself is obviously offers the greatest hardenability factor. So why steels normally, with the lower carbon, you can only through austemper very smaller sections. Whereas if irons, you can through austemper heavy sections, you've got a lot of carbon in the matrix and you've got a lot of carbon in the material. But then we add manganese. We normally have a look around about 0.3. This depends again on the foundry itself. So some of the smaller foundries will use a lot of pig iron, so they'll use a lower manganese contents, where higher volume foundries often use a bit more scrap steel, so they actually run a higher manganese content, maybe to 0.4, 0.45. Then we add copper, and then we add nickel. And in a worst case, if we have sections above 90 millimeters, we have to add molybdenum as well. We can through austemper sections up to 200 millimeters, even higher. We have proven we can do 250 millimeters. But this casting is around about 80 millimeters. So when we discussed and looked at the alloy, we went with something around a 0.75 copper and 1.8 to 1.9 nickel. So this is our site, ADI Treatments. Some of you have been there before. Some of you heard me talk about ADI Treatments before. Basically, we're based in West Bromwich, and we have the ability to heat treat castings up to tons. The most common furnaces we work are 920 millimeters wide, 920 millimeters high, and 184 millimeters, 1,840 millimeters. So relatively large furnaces, allowing us to heat treat large castings. So when, for example, we look at this lift arm for Atkinson Vos, in our furnace, we can heat 12 castings at the 55 kilos each. So only about 700 kilograms of castings in the furnace load, where we can heat treat up to 2 tons. But we have to look at how we load the castings and the size of the castings to optimize the loading, to minimize any movement of the casting and heat treatment, but also to ensure that we get the best throughput and therefore offer the customer the lowest unit price. Okay. Is it a video on that, or is it not working? Have you got a PowerPoint on, or is it a presentation? Okay, so you'll have to press buttons once for. So what we do is we load a basket up with the castings. In this case, the lift arm. Then we take the castings and we warm them up. We warm them up in about 600 degrees centigrade. This is just to assist with the economics of the process, because the next stage is to take the parts into the back of the furnace, which is at the high heat. So if we move through, they transfer through. We have to fortunately click it so. And then eventually they go into the back of the furnace. Okay, a bit further. And one more. So they get into the back of the furnace, and this is where they heat up to around about 900 degrees centigrade, so red heat. We do that in a carbon-rich atmosphere, so that prevents any of the castings from scaling up in the high heat. Once they're soaked in there for the set time, so we have a casting here which is 80 millimeters thick, so it'll be in the furnace for about 180 minutes. The rule of thumb is 60 minutes for 25 millimeters, so an hour per 25 millimeters. Once we've had the right soak, we come back out. And again, and the parts go into the quench. So in our smaller furnaces, we have 50 tons of liquid salt, which is agitated using impellers. The agitation works to actually move the salt around the castings to get an even quench throughout the parts. And then once again they're soaked in that salt for the set period of time, depending on the temperature we're using, they'll come out. We let the water, the salt drain off, and then we wash the salt off. Okay. Yeah. Okay. Yeah. So once we did our heat treatment on these castings, we then had to obviously prove out the properties. So as I said, there were 2 melts, which we did, even though I think there was only 10 castings made in the first order. There were 2 melts, and we had about 1.89 nickel in one and 1.99 nickel in the other. And as you can see from the results, the standard is 900, 608, and we're achieving 1,732, 970, 674. So these results are sort of on the limit of the standard. So yeah, we normally expect to be quite above it, but they are within the standard. So we're very happy with the results. Okay. And here we can see the microstructure we achieved for the ADI 900. This is a typical structure for an ADI 900, an ausferrite structure. Contains ferrite platelets and high carbon stabilized austenite. The austenite volume would be around about 35 to 40% for this grade of ADI. And the ausferrite gives it the ferrite gives it the soft, so that it gives you the ductility, and the austenite work hardens to give you the high fatigue properties that you want. And they work together to obviously give you that strength combination and ductility combination that you want in an ADI. Okay. Machining was done after the austempering. ADI is a tougher material, so obviously a lot of OEMs would prefer to machine before the heat treatment, which can be done, and a lot of our customers do that. But in this application, with the lower volume, and there were some very high tolerances, it was decided to machine after the heat treatment. Another reason it was machined after heat treatment was due to the fact we have this tie bar that you'll see in a minute. Obviously, we have to have the tie bar and stop the arms closing in the heat treatment, so that has to be taken out after the heat treatment. So that's, as you're doing that part of the machining, it was decided that all the machining would be done after the heat treatment. There wasn't that much machining. There were obviously the holes for the pins to go through, and then a couple of H7 holes in which their steel inserts were forced into. Okay. So those who don't know what a Unimog is basically a Mercedes vehicle, off-road vehicle, well, on-road vehicle. You can see it's a bit of a workhorse of a material of a vehicle, and as I say, the attachments we're talking about will either go on the front of this vehicle or the rear, and are used for lifting tree cutter machines, stump grinders, anything that you want to do for moving around, let's say off-road into forestry or onto embankments and likes of that. Yeah. So here you can see the casting itself. On the left-hand side, you see the actual tie bar in situ, and you can see there's no machining on that component. And on the right, you can start to see some of the preliminary machining, quite difficult to see, but the holes are now machined in, and you can see the steel inserts have been put in. Originally, again, this is design initially just put machined in holes, and when they tried to force fit the pins in, obviously they hadn't realized, like a bicycle pump, if you put your hole over the end of the bicycle pump and push, there comes a point when you cannot push it any further. And this was happening with the steel inserts. They'd made a nice circle, and then as they tried to push in the steel insert, obviously it was being pushed back against by the air. So they had to redesign the hole itself to ensure that as you push the insert in, air was allowed to come out. But these are things, obviously, often when you're, let's say, a designer at a university, a third-year student may not realize until it actually goes into the actual practice, and they learn from that. And this is, and then obviously next time they ever design anything, they'll realize that these things have to be taken into account. Yeah. So now we can see a part assembly of the component, and you can see the hydraulic arm there, and now you can see it's on that sort of vertical, and obviously there's no angles for it to seize in with. As if the arms were at an angle, initially were at an angle, as that arm was lifted up and down, it would seize, and actually that arm was enough force to bend those arms, and then obviously again it would cause a problem with actually operational use. Yeah. I don't think, am I talking too quickly? Because I might be finished. I might be as quick as a guy from Green Steel. And here we see the part in situ itself on the back of the vehicle. And this has already been in use for a while, so we know it does the job. Again, sometimes, and many of you will know this, a designer will put something on, and FEA will show something, and you put it into actual application, and the person using it will actually do something different than the designer has designed it for. So often you'll find that this will be not only used for lifting the actual wood chipper or whatever else, they'll be using it as a battering ram or something to actually push the tree over as well. So we can see that this has survived quite some time already, and works very well indeed. Okay. So maybe as quick as the other people. So again, the conclusions of this, the ADI has successfully replaced an 11-piece welded fabrication. So I think it's very important, again, when as foundries, whether it be iron, steel, aluminium, we can go out and we can say to the designers, you can change your fabrication to a casting, to a one-piece casting. Save yourself a lot of problems with regard to welding. Save yourselves a lot of problems of having to get 10 or 12 pieces of material together at one time. Because if you have one part missing, you can't make the component. You take away the risk of the welds. You take away the risk of, or the additional testing of the welds by putting in a one-piece component. The ADI was slightly lighter than the steel fabrication, only slightly lighter, but 2% is still important weight saving. Again, today engineers are looking for sustainability, and one of those sustainability things is to reduce the weight of components. So the part will give the vehicle or the machine a longer life. A lighter vehicle, a lighter component will last and make it last longer. Production cost was similar. Yes, initially there's an outlay for the pattern, which is often sometimes OEMs do look at patterns and go, that's a cost. But once you have that cost, the cost of the casting compared to fabrication is generally a lot lower in cost, and this was found to be the case. The actual casting removed all the issues they had with the binding of the hydraulic, the telescopic arms lifting and bending. So again, no problems in the field, no requirements for the engineers to go out and repair or replace components. And the production lead time was reduced. This is down to the fact that, yes, again, once you've got the pattern produced, but obviously this was a pattern was quite a low-cost pattern, can produce in 4 weeks. But even so, once the pattern's down there, produce the castings, you can get a casting produced in, say, typical lead time maybe 4 to 6 weeks, sometimes a bit longer. And then the heat treatment is maybe 1 week, and the machining can be done in a couple of weeks. So you could get a part from order to door to the OEM within about 8 weeks, whereas the welded fabrication was taking longer to do that. Don't ask me why, but I'm assuming it's basically struggling to get all the people, the parts together, all good welders. And I think that's about it, apart from the fact it did win Component of the Year, so it was very, very, very happy about that. So again, it was a joint venture between obviously the OEM, Atkinson Vos, the University of Lancaster, their engineering department, and then obviously the Foundry, the machine shop, and ourselves. Questions about the component, I'll try and answer that. or ADI in general, I can answer those. Hopefully. I could see James laughing. Maybe not. Okay, that's it, I think. You got. So when you're stamping the quench, then
So when you hello.
It's on the. It's for the video people.
Oh, sorry. So when you austemper in the quench, so how long is it in the bath for? Yeah.
For the austeming, there's a thing called a processing window. The processing window is literally it's more like an arch, and what that is showing the optimum period of time from the start to end where you get the optimum properties. And an arch, as you can see, an arch, basically what happens, the lower the temperature, the larger the wider or the longer the time period you have to optimize the mechanical properties. And the higher the austempering temperature, the shorter the period of time you have to time period to optimize the properties. Because what you have is what they call T1 and T2. T1 is where the optimum mechanical properties start, and T2 is when the optimum mechanical properties end. So T1 to T2 is shorter at higher austempering temperatures. But normally you're in the quench for, say, 90 minutes or 60 to 90 minutes for the grades that we're looking at here, the ADI 900. And for the higher grades, so the ADI 1400, because everything happens a bit slower, you have more. That's why it's a sort of wider, more time to get the optimum properties. You'll be in there for 3 hours, maybe even 4. But the whole point is that whether you've got a section of 20 millimeters or 100 millimeters, the time in the quench would be the same. So if I was austempering a component that had 20 millimeter section, it would be at the high temperature for maybe 1 hour and in the quench for 60 minutes. And if I had a section that was 100 millimeters, it would be at the high temperature for 4 hours, but it'd also be in the quench only for 60 minutes. Because because I've got this hardenability in the quench, I should be getting the surface and the core to the temperature before the transformation starts, and everything transforms at once, so that the processing time is the same. If that makes sense. I'll try and explain it to you on the back of a cigarette packet later.
Oh yeah, and in the old days, there used to be a sort of challenge between machining before the heat treatment and machining after the heat treatment. Are we better at machining after the heat treatment these days?
There are more tools out there that allow you to machine ADI after the heat treatments. There has been a lot more research done by companies like Sandvik and so forth, which allow you to do the machining afterwards. It really is down to the route. So if you have, we have a lot of our customers are from Germany, so they're quite happy to bring the work to us first and then do machining afterwards, rather than do some machining before, come to us and then go back and finish machine. It makes sense for them to do it that way. But I would say if I look at the tonnage we do, around about 60% is now machined before the heat treatment and 40% after. And it's just down to people's machinists. Are there any machinists in here tonight? Only online? My experience of machinists has been that they do quite like an easy life. They put products onto machine lines, and if it makes a noise and it squeals, they like to take it off the machine line and complain to the foundry that you've made the wrong material. And so we have to work with machinists to make their life as easy as possible. So I would say designer tools, or trying to say machine it before the heat treatment so they can do it in that soft state is always beneficial for them.
Great presentation. I'm interested in the quench again, but in terms of dimensional stability and risk of cracking, distortion. I saw on that component the arms were held in place by the tie bar. When you remove the tie bar, did it move?
No.
And I guess my other question is, how good is the tolerance in through the quench? And then in terms of things like cracking, distortion, could you just comment on that, please?
Say austempering is a low is a low distortion process, and cracking happens in heat treatment generally because what happens is when you quench from the high temperature into, let's say, oil, the surface transforms before the core. So that as a consequence, you get a stress variation between the core and the surface, and that therefore leads to the part. As you've got these variable stresses, the part will want to move and distort. And in the worst case, if the stresses are high enough, it will actually distort to a point of cracking. With the austempering, as I say, what we're trying to do is get the core and the surface to the temperature at one time, so you don't get those sort of stresses occurring, so you don't get that potential for cracking or the distortion. Obviously, it's not most of the distortion will happen in heat treatment, in austempering and other heat treatments. A lot of it is down to the way you put the parts in the furnace. If you take a bar and just throw it in the furnace, it will want to distort. So you have to think of how you're going to hold it in the furnace. Are you going to hang it, or are you going to lie it and position it? So we have to look at how we're going to load them to ensure that these parts don't distort through the actual heat treatment. Yeah. Yeah, you look at various parts again. Depending on volume of parts, you can come up with specialized jig systems, or you just look at whether you're going to hang the parts or lie them down and support them on 3 points. So we're doing if we're doing big gearings, we'll just obviously sit them on a tray and put them under 3 points, because as you can imagine, on 3 points everything is stable. So if you think of a milking stool, if you sit on a milking stool or a stool, it just doesn't move because the 3 points will find the center. Whether you're always, if you've got a table, you've got four points and there's one not quite, or the table will rock. Whereas on 3 points, rocking will stop. So you have to look at the sort of supporting your parts accordingly. I can distort your parts if you want to. It's not a problem. If it makes the machining easier.
Well, I'd like to thank Arron very much for coming and sharing this technical talk. I'm sure everybody found it very interesting. I do have a small gift for you, and I'd like to remind everybody that the council meeting is next Tuesday, and the next time we meet, it's for our quiz in January. Hope you'll all come, and in the meantime, I'll just get your gift.